Hello students, welcome to aimstoday online classes. This is a chemistry session. Here we are discussing about the chapter periodic classification. Okay, in this session we are going to say about trending of electron affinity and electronegativity of the elements in the modern periodic table. What is electron affinity? How does it is vary in a group and period of the modern periodic table, and in the same way about electronegativity also. Okay, first let us see about electron affinity, which is also known as electron gain enthalpy. This electron affinity is another important property of elements, just like electron ionization energy and atomic size of the elements. When an electron is added to an atom, energy is released in terms of electron affinity. So it is defined as the amount of energy released when an electron is added to an isolated neutral gaseous atom to make it an anion. So what is happening here? When an electron is given to a neutral gaseous atom, so that atom will gain that electron. Immediately after gaining the electron, it releases certain amount of energy out. The energy released by the atom while gaining this electron is called electron gain enthalpy or electron affinity. So atoms, they release certain amount of energy while gaining electrons, that we are calling as electron affinity, to say simply, right? So equationally we can represent like this. Suppose an element in the isolated gaseous atomic form X is taken. For that, if an electron is added, then that atom becomes an anion, that is negative ion. At the same time, certain amount of energy is released by that atom, that we call as electron affinity or electron gain enthalpy. Like the second and higher ionization potentials, second and higher electron gain enthalpies are also possible. However, the addition of a second electron to a monovalent anion as to make it A-2 is difficult because both have the same nuclear charge and A- requires more energy to overcome the force of repulsions. That's why you say the second electron gain enthalpy, therefore an endothermic process, and will be given a positive sign. What does it mean here? We told here electron affinity means the amount of energy released by an atom while gaining electron. Suppose we consider an element A. To this, if an electron is given, what happens? It becomes A minus, and at the same time some amount of energy is released out in the form of electron affinity or electron gain enthalpy, we told, isn't it? Now if we give one more electron to this ion formed A minus, what happens? Then that atom is already having one electron extra. To the same, if we provide one more electron, it may take that electron, but there exists some repulsions between the already existing electrons and this incoming electron. So actually while gaining this electron, atom may lose energy. But what is happening here? There existing repulsions between the electrons. To overcome these repulsions between the already existing electrons and incoming new electrons, so atom should consume certain amount of energy. That is why while taking second electron, atoms, instead of losing energy, they gain energy from the surroundings. Why? Because to overcome the repulsions between the electrons. That is why we say first electron gain enthalpy is negative. That means they release amount of energy, certain amount of energy while gaining first electron, whereas they take energy, they absorb energy while taking second and higher electrons, second and more than two electrons. Got it? That's why we say second electron gain enthalpy. Therefore, it is said to be endothermic process. And while showing in the equations, it will be shown with positive sign. Positive sign for the energy in the chemical equation represents absorption of energy. If the energy is mentioned with a negative symbol, that represents evolution of energy in the chemical reaction. Now, second electron enthalpy will be shown with the positive symbol, means it is absorbed by the atom while gaining second electron to overcome the repulsions. Not only second enthalpy, similarly, higher electron gain enthalpies are also positive, means those also endothermic processes. Right? Only first electron gain enthalpy is negative, that means that is exothermic, it releases energy. In the remaining all higher enthalpies, higher ionization electron affinities, energy is absorbed instead of releasing. For example, when an electron is added to an atom of oxygen to form O minus ion, the energy is released. While taking first electron, oxygen releases certain amount of energy which we call as first electron affinity. However, when second electron is added to O minus ion to form O2 minus ion, energy is absorbed. So equationally they are mentioned. Suppose for the neutral gaseous oxygen atom, if an electron is given, it becomes a O minus anion, and there certain amount of energy is released, and it is shown with the negative symbol C here. This represents exothermic process, means energy is released out. Whereas for the same O minus ion formed here, if a second electron is given, it forms O2 minus ion, but energy is absorbed by that in this process. See here, that is why electron affinity is shown with positive symbol, which represents absorption of energy, and hence this process is said to be endothermic. Okay. Now let us see the variation of this electron affinity in the modern periodic table. First let us see in periods how it is being varied in the periods of the modern periodic table. As the atomic size decreases and nuclear charge increases from left to right in a period, and hence the electron affinity values generally increases. We are telling electron affinity means amount of energy released while gaining electron. The element which readily gains the electron releases more amount of energy. Which element can attract the electrons easily? The element with the smaller size. So the atom with a smaller size can release more amount of energy. That means the atom with a smaller size will have greater electron affinity. So if you apply this property in a period, we know in a period from left to right, atomic size decreases, and hence we can say electron affinity value generally increases from left to right in the modern periodic table. In any given period, halogen has the highest electron affinity value. Yes, we told to say accurately in a period from left to right, atomic size decreases till halogens, and there will be a slight increase in the size for noble gases. So we can finalize it here. The halogen in a period, the halogen atom in a period will be having the highest electron affinity value. And if you say for inert gases, as they have completely filled valence shell, they do not accept any electrons. If there is no acceptance of electrons, there is no term about electron affinity. So we can say electron affinity values for noble gases are 0. Till then, they increase from alkali metals to halogens. So halogen of a period will be having the highest electron affinity value, and noble gases they have 0 electron affinity. Okay. Now, if you see second period element oxygen and fluorine, they have shown the size of the fluorine is somewhat smaller than that of oxygen. So, if the size is smaller and nuclear charge is greater, so this nucleus can attract the outer electron very easily. So, after attracting this electron, after taking this electron, immediately that releases a greater amount of energy than the remaining elements. Okay, and hence we say this is having the highest electron affinity, right? But there are some exceptions for this generalization. What do we say in general? In a period from left to right, atomic size and nuclear atomic size decreasing, nuclear charge increasing, and hence electron affinity increases. This is generalization. But there are some exceptions from this. Let us see what are those. On going from carbon to nitrogen in the second period, the values of electron affinity decreases instead of increasing. What we said, in a period from left to right, electron affinity increases. But in a second period, if you see from carbon to nitrogen, instead of increasing, it decreases from carbon to nitrogen. This is because there is a half-filled electronic configuration, the outermost orbit of nitrogen. So this half-filled configuration makes nitrogen more stable, ideal. So instead of readily taking the electron, it will be idle. It won't show interest in gaining the electron, and hence electron affinity value decreases. This is because of the half-filled electronic configuration of nitrogen. Whereas if you see for carbon, the configuration is 2p2 configuration. It is not half-filled. So it will be ready to gain that electron. It releases more amount of energy when compared to nitrogen. That's why from carbon to nitrogen, electron affinity decreases instead of increasing. Okay. One more, let us say, exception. Similarly, in third period, the value of electron affinity for silicon is greater than that of phosphorus. Actually, from silicon to phosphorus, it should increase because size is decreasing. But phosphorus having lower electron affinity than that of silicon. Here also the reason is same. The half-filled configuration of phosphorus. It has a 3p3 configuration. Means p subshell is half-filled, so that it attains some extra stability and hence shows less interest in gaining electrons. Thus, electron affinity is lower. Okay, in this way, because of half-filled electronic configuration, these elements of fifth group like nitrogen and phosphorus, they're having lower electron affinity values than that of fourth group elements, right? Next, one more exception. The values of electron affinity of inert gases are 0 because their outermost orbit has fully filled orbitals. Even for noble gases also we can see variation. Instead of increasing from left to right, till halogens it is increasing, and for noble gases it is becoming completely 0 because there is no question of gaining electrons in case of noble gases. Why? Why? Because they have completely filled outermost shell. So if that is completely filled, no question of gaining or attracting any other electrons, and hence there is no ionization energy for them. Okay. One more. In a period, the value of electron affinity decreases on going from first year to second year. So here, because of special electronic configurations, here from first year group element to second year also it is decreasing. The value of electron affinity of the elements of second year group is almost becoming 0 as their ns orbital is fully filled. For example, if we see sodium and magnesium, what is the valence configuration of sodium? 3s1 means it has one more electron vacancy in the s subshell. It may take electron and release certain amount of energy. Of course, actually these metals are not ready to take electron, but if an electron is given to sodium, it will release a small quantity of energy out, so that we call as electron affinity. But in case of second A group elements, their 2s their ns orbital, that means the outer shell s subshell is completely filled, so there is no chance for attracting electron. That's why for second A group elements, electron affinity is considered almost 0 because of their completely filled s subshell in the outermost shell. So there is no tendency of accepting electrons, and hence electron affinity values are 0 for them. Okay. Next, let us see how this electron affinity trending in a group. Electron affinity gradually decreases from top to bottom due to steady increase in atomic radius and the resultant decrease of the effective nuclear charge. So what happens in a group? We know in a group from top to bottom size increases. At the same time, distance from the outermost orbit to the nucleus increases, and hence nuclear force of attraction on the outer shells will be less. So they cannot attract electrons much easier. So electron affinity will be less for those. As the size increasing, electron affinity values decreases. So atomic size is inversely proportional to electron affinity, we can say simply. So in a group from top to bottom, atomic size increasing and hence electron affinity values decreases. So it is defining us how it is varying in the group from top to bottom. It decreases gradually in all the groups. Almost electron affinity values gradually decreasing because size increases. Okay. Here also there are some exceptions because of the size of the atoms in the groups. Let us see that also. The electron affinity gain enthalpies of oxygen and fluorine of second period, have less values than the elements sulfur and chlorine of third period. Actually, what happens in a group from top to bottom, electron affinity values should decrease because the size increasing from top to bottom. But here, fluorine is having less electron affinity than next element chlorine. Actually, fluorine should have the highest electron affinity, but chlorine is having greater electron affinity than fluorine. So, if you see second group, that is seventh group elements, electron affinity values, first from fluorine to chlorine, it is increasing. I observe this. So, after chlorine again, gradually it is decreasing as size increasing. So, why it is so? Why third period element chlorine is having greater electron affinity than the second period element fluorine in the seventh A among the seventh A group elements. Let us see the reason for that. This is due to small size of atoms of second period elements. Those are oxygen and fluorine. Because of small size, there exists some repulsions between the already existing electrons and incoming electron, and hence certain amount of energy will be utilized by these atoms to overcome these repulsions. That's why their ionization electron affinity values are somewhat less than the expected. Why? Because their certain amount of energy is utilized by those atoms to overcome the repulsions between the electrons. That is why they emit a certain less amount of energy than they expected. That's why these elements are having less electron affinity than the next element in that group. Okay, if you see here, oxygen is having less electron affinity than that of sulfur. Fluorine is having less electron affinity than that of chlorine. Here negative symbols represents the evolution of energy, exothermic process. And if you see the quantities, oxygen has less than that of sulfur, fluorine has less electron affinity than that of chlorine. So in each period, halogen is having the greater electron affinity we told. Among these halogens, now chlorine is having the electron affinity greater. So we can say chlorine is the element with the highest electron affinity among the periodic table elements. Okay, this is about electron affinity. Now let us see about one more property, electronegativity. When two atoms of different elements in a molecule share one or more pairs of electrons, forming a covalent bond, the pair of electrons are not shared equally by the bonded atoms. One of these two atoms attracts the pair of electrons more towards itself. For example, if you see a covalent bond formation between two atoms, one chlorine atom and hydrogen atom, both will share an electron for pairing and hence they form a covalent bond. But here, chlorine is having smaller size and a greater nuclear charge. Because of this, it will pull the electron pair towards it, and hence sharing will not be done equally between these two atoms. Okay, thus the tendency of attracting the shared pair of electrons towards one atom is measured in terms of electronegativity of that atom. We say this atom is having greater electronegativity and it is pulling the electron pair towards it more. Okay, now we can define this electron affinity as the tendency of an atom to attract the shared pair of electrons towards itself in a bonded molecule. So, if two different atoms are forming a covalent bond by sharing one electron each, there the shared pair of electrons are not equally shared between them. The atom, one with greater electronegativity, will attract the pair of electrons towards it more instead of being them equally shared. If we say A and B are two atoms, B is having greater electronegativity, then it will attract the pair of electrons towards it more instead of keeping them at equal distance. This tendency of an element to attract the pair of electrons towards it more is called electronegativity. All the factors that influence the ionization energy and electron affinity of the elements also influence the electronegativity, like size, electronic configurations, nuclear charge. These all factors which are affecting the ionization energy and electron affinity also influence electronegativity values. So, because of this reason, Mulliken proposed that electronegativity of an atom or an element is the average value of its ionization energy and electron affinity. So, according to Mulliken, electronegativity can be measured for an element by using the formula electronegativity X is equal to average of, that is, ionization energy and electron affinity. Okay. If electronegativity difference between two bonded atoms is less than 1.7, then the bond is said to be covalent in nature. If the electronegativity, if it is equal to 1.7, then the type of bond is said to be 50% ionic in nature. 50% ionic and 50% covalent. If the electronegativity difference between the two atoms in the bonded molecule is greater than 1.7, then bond is said to be ionic in nature. So, by knowing the electronegativity value, electronegativities of the atoms, we can predict the type of bond will be formed between those two atoms. Okay, if the electronegativity difference between the two atoms, if it is greater than 1.7, then they will form an ionic bond. If the electronegativity difference between those two is less than 1.7, then they will form a covalent bond. If it is exactly equal to 1.7, then we can say they form a covalent bond with 50% ionic character. Okay, that is about electronegativity. Now let us see the variation of this electronegativity in the groups and periods. First, let us see the variation in a period. Electronegativity increases along a period from left to right. This is due to the increase in the nuclear charge and decrease in the atomic size. Suppose if you say third period elements from sodium to chlorine, we know from sodium to chlorine size gradually decreases. At the same time, nuclear charge increases. We know sodium has only 11 units of nuclear charge, isn't it? What happened? What in the case of chlorine? It has 17 units nuclear charge. Nuclear charge is increased and the size decreased. And hence what happens? The attracting power, the tendency of pulling the bonded pair of electrons towards it increases. And hence we say electronegativity in a period from left to right increases gradually as size decreasing. And what in case of group? In a group, electronegativity decreases from top to bottom. This is due to increase in atomic size. So quite reverse to the case of period. What is happening in the group? From top to bottom, atomic size increases and hence electronegativity values decreases in a group from top to bottom. If you see first alkali group elements, lithium to cesium, we know from lithium to cesium size gradually increases. As size increases, electronegativity values gradually decreasing. You can observe here. What in case of again seventh group elements, halogens from fluorine to astatine they have mentioned here. We know from fluorine to astatine size gradually increases. As the size increasing, electronegativity value gradually decreasing. Okay, what we can summarize from this all, in a period from left to right electronegativity increases and in a group from top to bottom it decreases. Now which element will be having the highest electronegativity? We are telling from alkali metals to no halogens electronegativity increasing. So halogens are having the greatest electronegativity in all the periods. Out of these halogens, from top to bottom, electronegativity decreased. So the first element of halogens, that is fluorine. Fluorine is the element with the highest electronegativity among all. Okay, this is a trending of electronegativity in the groups and periods. Right. Thank you for watching our video. Please subscribe our YouTube channel AIMS Today for latest updates on recorded videos.